Let's talk about the field of a magnetized object. So what we'd like to do is understand the methods to determine the B fields due to a magnetized hunk of material. Before we start, let's look at some equations from a previous lecture. You recall that in free space we can actually relate the H field to B just by multiplying by mu zero. This is always true. Inside a solid, if you have magnetization, then the B field is related to both H and M, and so we have what we would call the B0 due to the free currents, and we would have this B mag due to the fact that the material has oriented dipole moments, which we associate with the magnetic dipole density. Many times we have this case of linear magnetic materials, and by that we mean that the magnetization is proportional to the H field. The proportionality constant, chi sub m, is the magnetic susceptibility. If we go back to our equation for B and we have a linear material, we can substitute in for m chi sub mh, factor out the h, and so we'll end up with this prefactor here relating B to H inside the material. If you come back here and if you're not inside the material, m is equal to 0, and so you're back to B equals mu h again. Well, we call this combined constant here mu, and so mu is equal to this set of parameters here, and mu is called the permeability of the material. Quite often we introduce a relative permeability, which is just mu over mu 0, and in terms of chi sub m it was just 1 plus chi sub m. So this is the relative permeability. Just in case you remember, this chi is dimensionless, and so therefore mu sub r is dimensionless. What we want to do now is derive what we call the bound current equations. And these bound currents are basically currents which will allow you to get the magnetization of a system and get the B fields just due to a magnetized material. To do that, we're going to have to use the magnetic potential. To start with, if you remember that if you have a single dipole that's sitting at the origin and is oriented in the direction of this vector m, if you're looking at a point, the field point, at some direction r hat and a distance r, so you have this r squared down here, then the vector potential of that dipole is given by this equation here. Suppose you have the hunk of magnetic material. The magnetization could be a function of where you are inside of this blob. The idea is to take a small volume element, which we call d tau prime, and relate the A at this point first due to this small volume, and then integrate over the volume to get the total A. And you're quite familiar with the definition of R, which is the position of the field point, r prime, which is the position of the source point, and funny r is the distance from d tau prime to the field point. We've got this magnetized material. It has this m of r prime, and so the dA of interest, due to the small collection of dipoles in this little volume element, is basically the density of dipoles times the volume d tau prime. So that's like a dipole moment that represents the average value of the m values within this small volume, and of course if we make it small enough that m will be uniform, and so we end up with a dipole given by this product here. Instead of talking about a little m, we then take this big M times d tau prime and stick it into our equation for the vector potential. And because we're only considering a d tau prime, this will be a differential of the vector potential. So again, it's mu 0 over 4 pi, and then this times this is the dipole moment, and then we cross it into funny r over r squared, because these are the vectors that describe the vector from the volume element to the field point. To get A, we just integrate this over the volume. So here it is right here. We just bring out mu 0 over 4 pi, and we integrate over the entire volume where the magnetization is non-zero, and then this is m of r prime crossed into r hat over r squared. Notice that we have an r prime here, We have an r prime in the funny r and in the funny r, and we also are integrating over tau prime. If we integrate over the prime variables here, our answer will not have any r prime contained in it. So here we again repeat our A. We're going to try to work on this a little bit. We start by recognizing that we can replace r hat over r squared with this gradient. So this is gradient with respect to the primed coordinates of 1 over funny r. Okay, so come up here, you'll notice that the answer to this gradient is basically this quantity right here. So we're going to replace that. So doing that then, if we rewrite the capital A and now put in our gradient for the r hat over r squared, then this is what we get. Okay, so now we're going to use one of our identities, and that is the curl of a scalar function times a vector function. Expand it, and you recall that you get this curl, and you get this cross product, which is g cross the gradient of f. F we're going to take as 1 over funny r. G is going to be our m. And I warn you that we have to be very careful with the signs in order to get the correct answer. So we are going to look at this cross product then of m cross the gradient of 1 over funny r. And if you come up here, that term is going to be this one right here. So we're going to have these two terms, and taking care of all the signs, we will end up with this minus the cross product of m divided by r. And if you look up here, that's related to this term here. The next term is the function f times the curl of capital M. So that's basically this term right here. So all we've done is taken our original cross product here and changed it into these two terms. We need another identity, and this is going to be used on the first term. What it is that the integral of the curl over a volume is equal to the cross product of the vector with the surface area vector, ds prime. And if you integrate this side over the entire surface s prime, which contains tau prime, then you get this identity here. Notice that there's a minus sign here. So going back to the term where we had minus this curl here, that can be changed to a surface integral. So this is over volume, this is over the surface. We end up then with the vector crossed into ds prime. So then we combine the two terms so that we have the original term, which was the curl of m over funny r, and then we now have this term right here that we add here. This was the second term here. We have this, what looks like fairly complex equations. We now want to look at this structure here and this right here in terms of the differential of the surface vector. Remember, that's perpendicular to the surface. If we go back to looking at the current density looks like, it's defined in terms of curl of a vector, and what this looks like is a volume current density which we identify as a current density J sub B, where B is the bound current. The term that looks like this, and the reason we have n hat prime, is that this quantity here could be represented by n hat times the scalar ds prime. So the magnitude of that differential. So all we've done is introduce this to get this factor here, which is the magnetization crossed into the unit vector normal to the surface. Well, that looks like a surface current density, and so we identify that with the nomenclature K sub B. The J and the K, are like we had for the bound surface charge and for the charge density inside that is bound for a dielectric. Just rewriting those definitions then, here is the bulk bound current density, and that will only be non-zero if the magnetization changes within the volume such that the curl is non-zero. The surface current density, the bound surface current density, is just equal to this value of m on the surface crossed into the n hat, which is the normal vector to the surface. So we can rewrite our vector potential in terms of those definitions. So here's our bulk J, Here's our surface K, and that will give us the vector potential. And what we gain from this are the equations for the bulk current density and the surface current density. So repeating that then, where we have the definitions that we have here, what it means, we can find the vector potential of a magnetic material because it's the same as produced by this volume current density and this surface current density. We don't have to integrate over all the tiny dipoles in the material, which would have to be done if you were unable to take these curls and cross products. The other thing is that from the previous lectures, we've dealt with finding B given a free current density and a free surface current density. If you remember, the line currents can be considered a special case of just current densities. In other words, I is the integral of J over a surface. This surface is not the surface of the tau. So in other words, if you had a surface like this, and you had a current density flowing through this, if you took J, this is J, and integrate over the area, that'll give you the current flowing through this region here. Well, the bottom line is that we can directly use the methods that we had before for finding the B field from current distributions by just using the bound currents as the sources of the B field. Another approach is where we can use the definition of A, which is this one up here. So this would be the star, star, star. We can use that equation directly to define A, and so therefore we can find B by using the cross product of A. Now let me just say that the major time you would actually use A is if you were to find A through a numerical method, in which case you would find a numerical B. So very complex distributions of magnetization could give you a numerical method to get capital A, and then you take the curl of that to get the B field. So let's take an example. We're going to take a uniformly magnetized sphere of radius capital R with a magnetization M, which is a constant. And the first thing we want to do is find the bound currents. And the second is to find the equivalent dipole moment representing this sphere of magnetized material, and then find the B field due to this magnetization. And we're interested in B both inside and out, so let's take a look at that. The first thing we do is turn everything around until we have the M vector along the z-axis. So that's what we show here. We're going to take the origin right at the center of the sphere, and that'll simplify life. The magnetization M sub r is a constant and is uniform. If we take the curl of that vector, that gives us a bulk J sub B current density equaling 0. The surface current density, on the other hand, can still have a constant M and still get a non-zero K. And so what that means is if the cross product is non-zero, then we'll get a K. If we recognize this as just the unit vector r hat prime notation, then what we're talking about is a unit vector at this point here for an angle theta. We take M and cross it into this unit vector here, then what we get is M sine theta. And then we have to determine the direction, and so we need the direction of M relative to n hat or r hat prime. And remember that the cross product is always proportional to the sine of theta. The length of this is 1, and so that's why we just have M sine theta. The direction of that vector, if we look at the relative directions of these, is in the phi hat direction. If you look up here, the phi unit vector gives us a circle if we just let it go around the sphere. And so at any point up here, we would end up with a component that's pointing in this direction that depends on theta. Let me draw this. This would be towards you and give you the direction of phi. You find that direction with the right-hand rule. Now let's find the equivalent dipole. We want to use that to determine the field outside of the sphere. If you look at this here, we have a differential of the dipole due to this magnetization, and it's going to be given by a current times an area. We accept the fact that this dipole that's due to M should be in the same direction as M. If we look at this, this should be in the z hat direction. If we look at the differential of current, what we're talking about is the current flowing in this ring that's on the surface of the sphere, because K is a surface current density. And so to find the K relationship to the current, you remember that the current is equal to K times a length. And the length we're talking about is the width of this line here. What is that width? If you have R, capital R here, and you have a small length here, you can relate that to theta. It'll be a d theta. So this width here is R times d theta. Then we come down here and we say, well, what's the area? Well, the area is this area here. It's the area of the loop. And so remember, we're talking then about a current that's flowing in a loop, and the magnetic moment is equal to the current times the area. Well, what's that area? Well, we need this radius right here. And so you use this triangle and find that radius. I think you can see that it's capital R times the sine of theta. So coming back to our equation here, the current is K sub B times dl. dl is this little width here, times the area, all in the z hat direction to get the direction of dm. We'll work on this in a minute. And here's our area. It's pi times that radius of the circle, which is capital R sine theta squared. So here we put in our dl, r d theta. We put in our area right here, and we just multiply everything together, and that'll give us dm. And I've already said that dl is r d theta. Collecting terms, if we can do it in two steps, but here's what we get. We get mr cubed, capital R, pi times the cube of sine theta d theta, all in the z direction. So what we've found so far is the differential in the dipole moment just due to this portion of the problem. So if we integrate from 0 all the way to pi, we will generate the total dipole moment due to this. To get m, we have to integrate. So here we have dm, so we're going to integrate that. Because of the fact that we've only got an angular dependence left, so we're going to integrate over theta. Rewriting that, here's our integrand here, integrating over theta. We'll keep the unit vector, which is in the z direction. But to do that integral, I won't go through the whole thing in detail, but we can make this simple substitution and change to cosine by using 1 minus cosine squared for sine squared. Put that in, and then it becomes a very simple integral, and we end up with this expression here for the dipole moment. What you see here is an m, the magnetization, and then if you notice, this right here is the volume of the sphere. We'll just put that in. The V is the volume of the sphere, and so not surprisingly, if we take the density of dipoles, and this is constant, then all we have to do is multiply the volume, and we'll get the equivalent dipole due to this magnetization. To find the B field inside and out, we first take this dipole moment and use that to find the B outside. If you remember that if you have a dipole moment given by this, the field of a dipole is given by the mu 0 over 4 pi, the usual factor. Here's the dipole moment, and then it depends on r is r to the cubed, and then the r component has a factor of 2 cosine theta, and the theta component has the sine theta. Putting that all in, I've left the r, capital R, into the equation, and if you wanted to, you could factor out these 4 pi's. So you end up with an expression for the B outside given by the dipole field. And so if you can imagine then the sphere having a dipole field outside oriented so that the dipole moment is along the z-axis. This is just the same equation repeated because we're going to use it. Inside, we start by assuming that B in is uniform and in the z direction. We're saying that B is going to have a simple relationship to the capital M vector. And the fact that M is constant, then we assume that B is constant. So here's our B in written as a constant coefficient in the z direction. So how do we find B in? Well, we're going to use B out. And we're going to use a boundary condition that we're going to derive later that says that the normal component of B is continuous at the vacuum sphere interface. What we're saying is that we have an interface where we have two different mu's, mu1, mu2, or chi1, chi2. The way that B changes as we go across here preserves the normal component. So if this is the normal component over here, it will equal the normal component over here. It says nothing about the tangential component. So if that's the case, then we can do this at a single point, namely on the surface of the sphere along the z-axis. So in that case, our unit vector is just the radial vector, and those are normal. If you take our B in normal, that's basically equal to B in times z hat dot r hat, and that's B in cosine theta. Since we're along the z-axis, we could have just set that equal to 1, and I'll comment on that later. B out at this position, we know that for this geometry along the z-axis, there is no tangential component for the dipole. The theta component is equal to 0. If we take our B up here, this is B outside, and we're setting r, little r equal to capital R, and we're only taking the radial component. So that's what we have down here, the B out at capital R for the radius, theta here. We set that equal to our expression that we had before. This is just the r component, and so we have this expression here. And notice that we have an r cubed and r cubed top and bottom. Okay, so that gives us B out, and so in order to get the B in, we just set these equal to each other. So here's the idea: you take the B out and set it equal to B in. B in, of course, was this. We could have really said cosine theta equals 1, or you could just cancel the two cosine thetas. So if you now solve for B in at the interface, so you have up here 2/3 mu 0 m. That's what we have here, 2 mu 0 capital M over 3. That's B in. Putting back the unit vector then, the B in is a constant field, which is what we said it would be, and it's in the z direction. If you wish, you could say m z hat is our capital M, so you could put it in this form if you wish, in which again is a constant. These two fields, B in and B out, are giving us a dipole field, and I really wanted to put a little r here. So this is the general B out, this is the B in. So if we take a look at what this looks like, I'll just draw it here. So you have a sphere, and inside the B field is uniform in the z direction like this. Outside it would be the usual dipole field. I'll just draw some streamlines. So we'd have something like this, something like this, like that. And of course these continue in the same direction. Notice that B is continuous across the interface. And the loops that we're talking about then are continuous around these streamlines. And so we have B behaving as we wish.